Mr. Tarrou, in this video we are going to review, deepen, and basically test your knowledge of the skills we just learned about the use of Venn diagrams, tree diagrams, in the binomial setting to help you answer probability questions. It's a type of question that you might see maybe on an AP test or an IB exam, or just the end of your chapter test dealing with this particular topic. In the description below, you will find links to timestamps to let you jump ahead to each of the, well, it's really 3 parts, A, B, and C, but each part has a couple of questions. So you can jump ahead to each of the individual questions we're going to deal with in this video. You're also going to find not timestamps, but links to old lessons I've done with these concepts as well, where I go more in depth into them because we're just introducing them for the first time. Let's get started. A restaurant sells lunch and dessert. Each customer will purchase either only lunch, only dessert, or both. The probability that a customer buys lunch is 0.75, or basically 75%, and the probability that a customer buys dessert is 0.4. Excellent. Find the probability that a customer chosen at random will buy. Will buy both lunch and dessert. Okay, you gave me the probability of a couple of events, lunch 0.075 and dessert 0.4. You're asking me for the probability that a randomly chosen customer chooses both, so we just add those, right? And if you really understood the concepts in this chapter, and this is truly review and not an introduction for some of these concepts, you should have been starting to kind of like scream through the camera. That's not right, right? A probability of an event occurring, even if this is a combination of a couple of choices here, has to be between 0 and 1, or between 0 and 100%. And of course that means we cannot have a probability that's equal to 1.15. So this should be a red flag that you kind of jump the gun here. This is not a probability of A or B is equal to the probability of A plus the probability of B. That rule for, a probability rule is only good for when A and B are disjoint events, meaning that there's no way that they can occur together. Well, that's not really what we have going on here. When you go to a restaurant, and it even says it in the problem, you can choose both. So, how are we going to find the correct probability for part A1? You can just use formulas, but remember our tools that we learned about Venn diagrams and tree diagrams are really, really handy, and they make a lot of these questions more intuitive and not necessarily something you just memorize a formula and plug it in and not really know what's going on. One of the tools for probabilities, and we'll be using this at some point through this question, is your tree diagram. But a tree diagram is really only appropriate when there's a clear sequence of events or choices. First something 1 happens and then something 2 happens. What's the probability of, a combination of things occurring together? That's a type of language which is good for when it's good to use a tree diagram to help you answer that question. But here it's just a customer coming in, a randomly chosen customer, and you just look at what they purchased. Either it being, only lunch, only dessert, or in case of our question, both. When there's not a clear, sort of like there's one trial, if you will, that randomly chosen customer that comes in, and then from that, you analyze, choices that customer makes. That's a situation where a Venn diagram is usually going to be your easiest tool to answer the question. Now, your sample space for your Venn diagram is represented by the rectangle. All the areas within this rectangle have to add up to be 1. The sample space, which is sort of that collection of all possible events or outcomes, it's not the circles. Sometimes we see Venn diagrams and we just see a bunch of circles and not a rectangle drawn or a box drawn around them. But it's actually, this is your whole sample space. And there's a few things going on here. We got a circle for lunch, which I'm going to reference as L, but I'm going to write lunch. Then you buy dessert, which I'll be from here on just saying D, as far as my notation goes. And you have that door open for both. So there's really like 4 areas here. There's this circle, which is the probability of lunch and not dessert, which I've seen multiple versions of sort of that complementary notation. There is this area, which is the probability of lunch and dessert, which is what part 1 is reviewing or asking. I'm just doing a big old review here. You have a third part here, which is going to be your probability of buying dessert, but you're not within the circle for lunch. That's the probability of not lunch and dessert. And then that last area, which is here, that inside the rectangle but not within the circles, that's your probability of not buying lunch and not buying dessert. Well, thankfully here, again, we don't consider someone a customer of a restaurant if they don't buy anything. So the customer has to buy either only lunch, either only dessert, or both. If they're just going to come in and sit down and drink water, we're just going to kick them out. So we already know the area of this region. Well, I'm trying to think of a color that's going to show up, but I'm just going to stick with white. That is going to be 0. So when we added that lunch and dessert and got a probability of 1.15, well, there's another rule for combining probabilities, which is the probability of A or B is the probability of A plus the probability of B minus the probability of A and B. That overlapped area gets counted twice. That's why this number is over 1 or 100%. So here we already got this answer. The probability that someone chooses lunch and dessert is equal to 0.15. That's it. That just sort of fell right out of the Venn diagram, and I didn't even seemingly do any math. That's pretty cool. Now there's going to be lots of questions. So let's go ahead and just fill up this Venn diagram that we have now that we have it started. This entire lunch circle, we were told that the probability of someone buying lunch, now watch this language too, they either buy only lunch, but then the probability of buying lunch, see the word only is not there, so this includes that person buying lunch only or lunch and dessert. So these two parts have to add up to be 0.75, which means that this part here is therefore has to be equal to 0.60. I'd put a 0 there too, but I'm a little bit limited on space. So 0.6 plus 0.15 is that entire circle for representing lunch in our Venn diagram of adding up to 0.75 probability. Dessert was 0.4. Take out the 0.15 and we have 0.25. Okay, so now with this as here's our tool, I bet it's going to come in really handy for some other parts of this question. Yes. The probability that the person buys lunch and dessert is 0.15, and the probability of that person only buying dessert, so basically dessert and not lunch, is equal to 0.25. Now let me just double check, make sure I didn't write something silly. Perfect. Now notice I did not write the probability of dessert. The probability of dessert was given to us, a purchase of dessert was given to us as 0.4. If I wrote the probability of dessert equals 0.25, that's in direct conflict with what's given to us in the problem. So now the tests like AP will generally want you to write a full sentence in context meaning of this question, like, you know, a customer chosen at random will have a 0.15 probability or of purchasing lunch and dessert. A randomly chosen customer will have a 0.25 or a 25% probability of purchasing only dessert. Or you can have this written in your probability notation. It just depends on what your teacher and what the test is expecting, so make sure you know that before you go on to that test. Let's go on to part B right now. Part B, on a typical day, now we're told that by past records we know that 150 customers come into the restaurant on a typical day. Well, expected number, that phrase in statistics and probabilities means average or a mean. And it's okay for this to be a decimal, to say that, you know, we understand this is a calculated average. When I say that, you know, maybe I come up to 103.7 customers. There's no reason or need to round off that to maybe 103 or 104. So, lunches. Well, you have a set number of people coming in of 150, and you have a probability of that customer buying lunch. It's 0.75. Now, there's all kinds of formulas for calculating means. Just like here's 10 numbers, find the average, add them all up, divide by 10. Mean, standard, you have a mean for discrete random variables, a mean for continuous random variables. This is a discrete random variable. You have a set number of people coming in, and you have a probability of some event occurring. So this is the mean of a discrete random variable. Let x be the number of lunches sold on a typical day. Well, then the mean of x is going to be equal to 150 times that probability of them buying lunch, which is 0.75. And when you multiply those two numbers together, you get 112.5. And be careful that when you introduce a variable that you define it, be careful that you are going to write this answer in a format that is acceptable and needed from your teacher or test. Are you going to be allowed to just put a number down, or are you going to have to rephrase this as, on a typical day, we are expecting that 112.5 customers will purchase lunch. Okay, but I'm going to just leave it like this with the notation. Find the probability that more than 120 lunches will be sold on a typical day. Well, probabilities, right? Defining the probability of an event actually occurring. Now, recognizing what this setting is, we talked about someone buying only lunch, only dessert, or both, but this question is only focused on whether or not a lunch will be sold. So this question is really only about, did a lunch sell or not? Well, that's only two outcomes. And I'm kind of out of space here, so I'll just verbalize this. You need to read this question, and actually really for part one here as well, and recognize that you're looking at a binomial setting. Now, if you're taking like say AP statistics, this should have been like really just hammered into you really, really strong. I think sometimes like the IB book that I taught out for the last couple of years, they kind of like, I don't know, muddied through this a little bit. It was a little bit more vague, less specific than my years of teaching AP stats. But a binomial setting is when there's two outcomes. You either sell lunch, or a customer either buys lunch or they don't, or you sell lunch or you don't. There's independence. Is the probability of one customer buying lunch going to affect the probability of the next customer buying lunch? You have to have independence. You have to have a constant probability, and we're going to assume that that probability stays at a constant 0.75 for that probability of a customer buying lunch during a typical day. And you need a constant n, or a set number of observations. Well, that set number of observations is that 100, where'd I go? That 150 customers cross. So we have two outcomes, lunch or no lunch, constant n, or a set number of n, that 150 customers that come in during a typical day, that constant probability of 0.75, and the assumption that one customer buying lunch is not going to affect the next customer buying lunch. We have that independence. And with all that being said, we have this command in our calculator, and I don't know what calculator you're using, but binom CDF, it's NPK, and it is a binomial cumulative distribution function. You can find it usually like at the T84 by doing second distribution. And this command will basically equal the probability that x is less than or equal to some k. So this n is going to be our number of trials. That's going to be the 150 customers coming into the restaurant. P is our probability of success, and here we're considering them buying lunches. So our probability of success is going to be that 0.75, and k is, in this case, that one, well, it doesn't have to be equal to 120, but it's that number of successes that you're looking for. And now software is always changing, but calculators do count down. Like a T84 will generally only find probabilities that count down. So we're looking for, again, with x being the number of lunches sold, we are looking for the probability that x is more than 120. And this is a discrete random variable. So the probability of selling one specific lunch has a value not equal to 0 like with a continuous random variable. Well, that's counting up. Your calculator is probably going to be set up to only be able to count down. So you have to recognize that if you have 150 people coming in for lunch and you want to find the probability that you sell 121, 122, 123, and up to 150 lunches for those 150 customers that come in. Well, that's going to be equal to 1 minus the probability that x is less than or equal to 120, right? More than 120. So that language is not equivalent to this notation. This would be something like find the probability that you sold at least 120 lunches. And since the probability of selling 120 lunches has an actual probability, not some theoretical 0 like you have to assume with continuous random variables, you would need to adjust this notation to be 119. Okay, so be careful with this if you haven't had that pointed out to you from your teacher or from understanding from the reading of your book or such not. So we want to find the probability that the number of lunches sold is greater than 120, and the opposite or the complement to selling 121, 122, 123 up to 150 is 120 down to 0. Which means we're looking at 1 minus binom CDF 150, 0.75, 120, and that comes out to be 0.0628. And this notation here, that probability that x is greater than 120 is equal to this number, might be enough, or you might need to say something like that on a typical day when we have 150 customers come in, we should expect, or that the probability of selling over 120 lunches is 6.28%. Make sure you format your answer in the way that is going to get you the most number of points from your teacher. Part C coming up right now. Alrighty then. Part C, last two questions. Past records show that 57% of the customers at this restaurant are female and 85% of them buy lunch. We're bringing in a new variable. Now we're talking about gender. If a customer is selected at random, find the probability that a customer is female and buys lunch. Reread this again. Past records show that 57% of customers are female and 85% of them buy lunch. Well, I told you that you have two sort of graphical tools for at your disposal to help you find probabilities: Venn diagrams and tree diagrams. And Venn diagrams, basically sort of like one trial and with multiple choices or outcomes. Venn diagrams is when you have sort of like a sequence of events. And it doesn't necessarily seem maybe at first that there's a sequence here, but 85%, not 85% of the customers, but 85% of them. Well, who's them? Is it the males? No, it's the females. 85% of the females buy lunch. So while the probability of buying lunch was what? 75%? The probability of buying lunch, given that you're a female, is actually 85%. So this isn't really part of the question, but this language says the probability of buying lunch, given that you are a female, is equal to 0.85. 0.85, and I can't help but just going off on different tangents when I make my videos. That's why I always seem to be a little bit long. Let me just stop this for a second and ask you, is the event of a customer buying lunch independent of that customer being female? The probability of someone buying lunch, we were told, was 0.75. The probability of someone buying lunch given that they're female is 0.85. Now you might snap and go, well, of course, you buying lunch or not has nothing to do whether you're male or female. Well, that kind of sounds right, but in the type of food and where this restaurant is, maybe that has something to do with it. They're really not independent. An independent event is an event that's, one event is not affected by another. Of all the customers that come into this restaurant, 75% of them buy lunch. Of the females, if that customer coming in is female, that's going to change the probability of them buying lunch, which is 0.85. The fact that these two values, the lunch and the lunch given that they're female, are not equal means that these are actually, though at face value doesn't seem like they should be, they're actually dependent events. The probability of being a female changes the likelihood of you buying a lunch. And think about that. Of them, I'm not going to consider whether or not you buy lunch unless you're female. So this is not a situation where you're going to want to use a Venn diagram. This is a perfect opportunity to use a tree diagram. Your customer comes in and they're either male or they're female. And then we know that past records show that 57% of the customers are female, so we're going to put this in as 0.57. That means that this branch is 0.43. And then from there, we're going to look at whether they bought lunch or no lunch. Lunch or no lunch. And if the person came in was female, then the probability of them buying lunch is 0.85, and the probability of them not buying lunch is 0.15. And the question says, if a customer selected at random, find the probability the customer is female and buys lunch. The probability the customer is female and buys lunch. Well, if these were independent events, that would be your notation for finding the probability. The probability of A and B is equal to probability of A times the probability of B, or in this case, female and lunch. But these are not independent events. What's happening is, first, that customer comes in and we identify them as either being, they're identified as either being male or female. So that first branch happens. And then we multiply along the branches. When you have a tree diagram, I'm writing the formula as well. But once you set up the tree diagram, you're like, female and lunch, you just multiply along those branches. In proper probability notation, it's the probability you're female, and then it's the probability that you buy lunch given that you're female. So that's going to be 0.57 times 0.85, and that comes out to be, not right off the top of my head, 0.4845. So basically on a typical day, the probability that a customer is female and buys lunch is equal to 0.4845 or 48.45%. So yes, I got the last part 2 of C coming up right now. And last but not least, the guys. A male customer is randomly selected. Find the probability that he buys lunch. Now, I'm not given any information about the probability of a male buying lunch. We just talked about that the buying lunch and being female are not independent events, so I can't just jump to a conclusion of what the probability is that a male buys lunch because, well, gender affects that probability. But looking at our Venn diagram and pulling from the information that we had given to us in the previous setup of the problem, this is a Venn diagram that represents all the possible outcomes. You're male and you buy no lunch, you're male and you buy lunch, you're female, then you buy lunch, or you're female and you do not buy lunch. And if this is the Venn diagram of all the possible sort of sequences here that we can have, because remember, we're not considering anybody a customer is not someone that doesn't buy anything, then we were told that, and I have it broken up here, right, but we were told that 75% of the customers bought lunch. And we have, highlighted in red here, 2 branches, not that one, that end with someone buying lunch. And since we know the total probability has to be 0.75, then actually all we have to do is then recall that, continue to use our Venn diagram, and make sure that the 2 branches that end with someone buying lunch, regardless of their gender, make sure that adds up to 0.75. So here we go. We have the females coming in. And buying lunch. We already know that answer, but I'm writing it out anyway. Plus, we have the males coming in, so there's a 43% probability that the customer is male. We don't know then what the probability of that male is buying lunch, so that's going to we'll just call that, I don't know, A. But the females buying lunch and the males buying lunch has to add up to that total of 0.75, which is, of all the customers that come in, 75% of them buy lunch. Now, grabbing a calculator, we have that 0.057 times 0.085 comes out to be 0.4845 plus 0.43a is equal to 0.75. 0.43a, subtracting both sides by this 0.4845 gives us that 0.43a is equal to 0.2655. Dividing both sides of this equation by 0.43. Yields an A value of 0.617. Okay. And that is basically probability of buying lunch given that you are male, if you're just writing it with probability notation. I'm Mr. True. Bam! Go do your homework.